Okay, I guess we'll just get started now. Let me share my screen. Okay. All right, hello everyone. I'm going to talk about the core autonomy. So just setting up for the exercise should only take 5 minutes, so you can do it while I'm talking. So this part you should have already done. You can do it now. But if you already did it, you should update again because I've added these slides to the repo and also made a few changes so the exercise is easier to do. So if you just go into Core Central and then Git pull, and then just run WS tool up again, you can either do it while I'm talking or when we start the exercises. And you should get the slides because there's some stuff you can copy and paste for the exercises. So the Core Autonomy stack is a set of software that's supposed to provide basic autonomy functions for drones, like takeoff and landing, obstacle avoidance, and a GUI for interacting with the drone. So the motivation is, basic set of software. It's supposed to be a starting point for new projects, so you don't have to. There's a lot of things, I guess, to set up if you want a drone to fly. This kind of makes it easier if you already have some of that stuff. It's also to avoid everybody having their own setup to make things easier to share between projects. And it's also supposed to be easy to use. And the components are kind of split up so they're easy to replace with your own project specific components. Just a brief history of the core stack. The code kind of started out in the Autel project, which was a small camera only drone. It was basically supposed to take off, fly around, avoid obstacles, and then land. And the code was messy at this point. A lot of it was in a single node. And then I also got put on the Sub-T project in addition to Autel. So the Sub-T drone had a LiDAR instead of cameras. But basically it also needed to take off, follow some waypoints, and then land. So a lot of the functionality was similar. So at that point, I kind of split the packages up so they could be reusable as reusable between these two projects as possible to try and make things easier for myself. And a lot of those packages are called like local planner trajectory controller. They don't have the core prefix. So those are outdated now if you see them around the bit bucket. And then I think after the first round of the Sub-T competition, Basti asked me to put stuff into the core autonomy stack. So then I kind of cleaned up the code a little more and put all those packages are now called core underscore whatever. And other people besides me have since been adding core packages. I guess this is out of date, but here's some drones that are using the stack. Sub-T hex rotor, small quad rotor that we don't use anymore, and the MBZ M200, M210. Also another motivation for the core stack was to make things easier for a safety pilot, like make being a safety pilot less stressful. So this was the original Sub-T drone. I think it was like 7 kilograms. It's a hex rotor. It doesn't have any prop guards. We were flying around like constrained mine environments. And so a lot of the functionality is to make it easier to recover the drone if it gets in a bad position. So there's functionality like you can easily make the drone pause and just hover in place, or blindly backtrack along the path it just flew to get it away from whatever it was near. And you can trigger a landing also very easily. So back when we were using this for the Sub-T, I actually never had to take over totally manually and fly it with the joysticks. I only triggered those types of behaviors. So yeah, the outline for the talk, I'll just go over an overview of the architecture, each node in the stack, then talk about how to use the stack on your own drone for your own project, and then we'll do an exercise together. So this is the overall architecture of the stack. Here's the actual drone and the sensors, and here is the base station GUI that you actually interact with everything with. So basically, your base station commands go into the behavior tree, which is the piece that kind of decides which actions are performed, and behavior tree communicates that kind of information to the behavior executive, which actually implements the individual actions. And then there's these three nodes here, which all publish some type of trajectory, either a takeoff landing trajectory, a fixed trajectory like a circle or racetrack, mainly for control tuning. And the local planner actually publishes little pieces of the trajectories to avoid obstacles locally, and has an interchangeable map interface depending on which sensor setup you're using. And so those trajectories go into a trajectory controller, which outputs basically a single point for the drone to follow. It's an odometry message, so it has position, orientation, linear and angular velocity. And then that tracking point message goes into the various controllers as a pose controller, which takes the position set point and outputs a velocity command. And those commands go into the drone interface, which is actually in charge of sending commands to whatever drone you're using. So basically there's a common interface and you implement it to work with whatever drone you're using. There's support currently for DJI, Pixhawk, and just a pure Gazebo simulation drone. So the state estimation is not included in the diagram. It's kind of assumed that you'll be getting some kind of state estimate odometry message. And there's one node that I'll talk about later that can help with that. Okay, so now I'll just go through each node and give a little more detail about each one. So the first thing is the behavior tree. It's basically an alternative to a state machine and decides which tasks to perform. It's made up of condition and action nodes. So each node can have a status, either success, failure, or running. So green for success, red for failure, blue for running. Condition nodes can only have success or failure, not running. So condition nodes basically tell you the state of something in the world or the drone. So like, for example, there's an in-air condition which tells if the drone is in the air. In this diagram here, the conditions are these nodes with the round, they're these oval nodes, and all the other nodes are action nodes, and they're rectangular. So the action nodes with the text on them are ones that you would define what actually happens when these actions are triggered. So like, for example, right now the go home action is active. So the behavior tree would notify the behavior executive, and then the behavior executive would to perform whatever actions are necessary to actually go home and report back whether it's successfully at home. If it's still on its way there, it'll be running. And if it couldn't make it home, it would report failure. And then there's these special action nodes. Sequence nodes have an arrow. Fallback nodes have the question mark. And basically these control the flow of which conditions and actions are getting checked. So the way fallback nodes work with the question mark, it checks each child node from left to right. And if one of its children is successful, then this node also returns success. So like in this example right here, visited destination, this condition is true. So since it only requires one of its children to be successful, then it doesn't even bother checking the rest. It just returns success. Sequence nodes, the arrow nodes, also check each child from left to right. But for it to be successful, every one of its children has to return success. And if one of its children returns failure, it returns failure. If one of its children would return running, it would also return running. So here's a failure example. Here's a running example. So it's only when all the children return success that it returns success. And these nodes are basically used for the logic that determines which actions become active and which conditions are checked. So I guess one of the main advantages over a state machine is that you basically have to implement the functionality for all your actions and implement all the conditions, and you can compose the tree in any way you want. So you basically build the overall behavior out of the simpler conditions and actions. Whereas with a state machine, if you wanted a new behavior, I guess you'd add new edges that go to different states. And instead of just modifying a config file, you'd probably have to add some code, like some if statements to check when the transition should happen to the other state. So here, the config file is designed, so the behavior tree is designed to be easy to reconfigure. So the config file is supposed to look like the actual output of the tree. So like the root node here is a question mark. Right there it is. It has two children, the two arrow nodes. Condition nodes are surrounded by parentheses to look like the oval nodes. And action nodes are in square brackets to look like the rectangular nodes. Yeah, and as part of the exercise later, we'll be modifying the tree. So this will be useful information. There's also a GUI for debugging your tree, where you can choose what you want the return value of the different nodes to be. So you can just set conditions to success or failure, actions to success, running, or failure. And you can also check what happens if no message gets published at all. Basically, the behavior is you have a second to respond, or else it'll consider it a failure. But actually, the behavior tree, the behavior executive takes care of publishing everything at the right rate. So you don't actually need to worry about that much anymore. Yeah, so there's also a GUI. You can see the state of the behavior tree and send commands. So each one of these commands is basically connected to a condition in the behavior tree for triggering each of these actions. This part of the GUI is for sending fixed trajectories, mainly for control tuning, like figure eights, racetracks, and circles. I think other people have added lines and lawnmower patterns now. Yes, the first part of the GUI is the part that lets you send commands, and the buttons are generated automatically from this YAML file. So for example, the takeoff, this is what the name of the button will be, is takeoff. And the condition it controls is takeoff commanded. So I guess it's hard to see, but this condition here is called takeoff commanded. And when you press one button within a group, all other conditions will become false. So like if you click takeoff, everything else will be false, land will be false. So that way you don't have conflicting commands being sent out. Then trajectory part of the GUI is also it's another YAML file to define the attributes of the trajectory. And then basically the attributes and their values are put into a dictionary and sent to a Python function. So if you want to add a new trajectory, you basically just have to write a Python function that checks the right attributes and forms a trajectory based on those values. Okay, so the next node we'll look at is the behavior executive. So it basically receives which actions are active from the behavior tree and then sends back a status, either success, running, or failure. And it also sends back the status of conditions. It sends back all conditions all the time, whether they're true or false. So it doesn't need any feedback from the behavior tree for those. It's always sending. Yeah, here's just a quick example of how you would implement an action in the behavior executive. For the exercise today, we'll only be implementing a condition. So we won't have to do this. Basically, you would check if the action is active. The tree would tell you that this action object dated and this would return true. Then you would set the takeoff action to running so that it knows the behavior tree knows that something is going on. There's been a response. This function tells you whether the status of the action has just changed. So basically, when it first becomes active, this will be true. And also when it transitions from active to inactive, this will be true. But since we're only checking active, we're only triggering an action when the action first becomes active. And so we're just sending out a service call to make a takeoff happen. And then this is published. This variable is updated by some feedback from the takeoff landing node. And when it says it's complete, it sets a condition, the takeoff complete condition to true, and also sets this takeoff action to success. And yeah, we're publishing the action to the behavior tree. So the next node are these three all published trajectories, but have kind of different purposes. So the first one is publishing a takeoff and landing trajectory. It just publishes a vertical line. And it checks, so the tracking point moves up to the top of the line to make the drone take off. And then it checks for whether the takeoff is complete by checking if it is within some threshold distance of the tracking point for some threshold amount of time. So like it has to be within 20 centimeters of the tracking point when the trajectory is moving for like 20 seconds, or well, probably like 5 seconds or something. Landing is similar. It doesn't know where the ground is, so it just publishes like 1,000-meter downward trajectory and checks for completion when the drone has moved less than some distance for some amount of time. So I think in sub T, it's like if it doesn't move, if it moves less than 2 centimeters for like the last 5 seconds, then the landing will be considered. The next node here is the fixed trajectory generator, which is mainly for cold tuning. This will just publish one of these patterns, circles, racetracks, or figure eights. So you can see how well your tracks the trajectory. The next one is the local planner. This actually, so the previous two are publishing complete trajectories that will be run from start to finish. The local planner is publishing smaller pieces of trajectory that locally avoid obstacles, and it's so it's constantly planning from a new point, and then the output trajectories get stitched together by this trajectory controller node. So it has a library of trajectories to choose from, and basically tries to avoid obstacles and follow this blue line, the global plan. And yeah, each of these green arrows here. So the way the local planner works is it has a bunch of submaps basically. So it has two map representations, a LiDAR map and a disparity map. The LiDAR map basically stores a point cloud, the Velodyne scan from each one of these positions, puts it into a KD tree, and then checks each point in a trajectory against each of these KD trees to see if there's a collision. And for the disparity map, it's using Getesh's drone disparity map, which basically does a similar thing, but with disparity images, where it keeps a list of them and then checks within each image to see if there's a collision. And yeah, so the set of trajectories are defined by a bunch of accelerations. So if the drone is still, like there's zero velocity, the accelerations would be going outwards in all directions. But if the drone has some forward velocity, then since the trajectories are defined based on accelerations, it'll change the shape of all the trajectories based on the velocity. So it kind of is supposed to make the drone's motion a little smoother since it's factoring in acceleration. The trajectory library is also defined by another YAML file. So you can set the frame that's in, the magnitude is the magnitude of the acceleration. So like, how many meters per second squared. This is the direction of the acceleration. So this one would be going straight forward. This one would be going like to the left or right, 45 degrees. And then HT is the horizon time, so how far ahead the trajectory will be going in time. So it basically affects how long the trajectory will be. And then DT is the discretization along that horizon time. So like maybe you do a point every 0.2 seconds, 4 or 5 seconds total. And then there's also velocity. Yes, like I said, you can swap in different map interfaces, either a LiDAR map, and I guess the previous talk they made an octomap representation. And basically, there's a one class interface that you have to extend from. Implement, I think, two or three methods. Which basically one is checking for collision, one is clearing the map, and I think that's pretty much it. Yeah, and it's using plugin lib, which lets you swap in, basically lets you dynamically load whichever library you want with a ROS launch printer, so it's easy to switch between map representations. So first, the LiDAR map is like I said before, a bunch of KD trees, checks each one for collision. If there's no collision, then the trajectory is collision free. And the local planner will basically choose whichever collision free trajectory gets it closest to the path it's trying to follow. Disparity map is using Getesh's disparity expansion stuff, like I mentioned. So the trajectory controller is what actually takes in the trajectories published by these three previous. And so a trajectory is actually made out of X, Y, Z, yaw, and velocity. So if you have all those, you know where the drone should be in time since you have the velocity. So it basically moves this blue point. This is the tracking point that the drone is trying to follow, and moves it along in time and publishes what the velocity and position and orientation should be at that time. for these takeoff and fixed trajectories, it just takes whatever trajectory you publish, that's the whole trajectory, and that's the final thing. For the local planner, it breaks things up into segments and stitches them together. So it basically stitches by taking the closest point. Well, you publish a new segment that has some start, and it looks at how close that start is to each point on the trajectory and stitches it at the right place. So if you're always planning from the look ahead point, which is also published from this node, the look ahead point is exactly on the trajectory. So there should be no ambiguity about where it gets stitched together. Yeah, so here the tracking point is in blue. The look ahead point is some fixed time ahead in the future, so like a second away from the tracking point, to give your planner enough time to plan before the tracking point catches up to it. And so since the tracking point just follows, it just moves based on time, you can also pause it. So it'll just stop moving where it is, and hopefully the drone will then hover in place. Or you can make it rewind, which makes it backtrack exactly along the path it just was. So if you have a good state estimator, this basically makes the drone blindly backtrack along its path. Yeah, and it's mainly for the safety pilot to like get the drone out of dangerous situations. But in Sub-T, we also have an autonomous trigger for this. So sometimes it can be useful for autonomous behavior also. So the next few nodes are the controllers. They both use a common PID controller class, which works the way you would expect it to. So basically, the input of the post controller is a position, and I think also a velocity, which it can use as a feed forward to the velocity controller. So then the post controller outputs a velocity set point based on the position error, and also I think a feed forward. Then the velocity controller outputs a roll pitch yaw rate thrust command to send to the drone interface. Oh yeah, so this PID class uses dynamic reconfigure. So here's like you have the post controller controlling XYZ yaw, velocity controller controlling velocity, XYZ yaw rate. And you can use RQT reconfigure to tune each one of those parameters. It's mainly useful for sim, not in the real flight, because if you're trying to scroll through this GUI and your mouse is over one of these sliders, it'll move the slider, which is kind of unexpected. And if you try to instead type numbers in here, I think the numbers get sent to the node when you lose focus of the text entry. So like if sometimes Ubuntu has pop-ups like software updater, if one of those things popped up, then whatever number you happen to be in the middle of typing will just get sent. So I never use it for real life, but it makes testing things in sim go quicker. So the next thing is the drone interface. This actually communicates with whatever drone you're using. So there's a bunch of functions that are optional that you can implement. The first is request control. So this is like on a DJI drone, I think you would actually, the DJI function is called request control to put it into a mode where it's ignoring like the user's joystick commands and just going based off of the commands from the computer. On a Pixhawk, you'd be putting it in offboard mode. Arm and disarm, make the prop spin up or not spin up. And then some checks for whether it's armed and whether you have offboard control, which are mainly useful for updating conditions in the behavior tree. And then you can also implement one or more of these command functions. The most common ones are probably pose stamped for position set points and attitude thrust for roll pitch yaw rate thrust. The way those things are sent to the drone vary based on whether it's a DJI or a Pixhawk or whatever. And basically all the different types of commands, I just took MAV messages, had a bunch of different control commands, and then I have a velocity set point and a position set point. So for state estimation, most state estimators using ROS usually output some kind of odometry message. That's kind of what the core stack expects. As long as the frame ID and child frame ID are actually correct, and the TF tree is set up for those two TFs, all the TF lookups in the core stack should be correct. So as long as your odometry message is valid, it should work with the core stack. But in case, sometimes there's some transformation you want to do. There's this core odometry transform package, which takes as input an odometry message and can do various things to it. So sometimes state estimators will just set the frame ID and child frame ID to just some string and not actually publish the TF. Like I think Vinzimano does that, and Gazebo also does it incorrectly with the ground truth plugin. So this node can just change the frame ID name, like basically overwrite it with a new string that you are publishing a TF for. Sometimes you want the odometry message to actually be transformed into a new frame. So if the frame ID is correct, but you want to transform it into a new frame, this node can also do that. It can also restamp the trajectory. So sometimes the state estimator will be doing some kind of weird time sync thing and just stamp it with a time that's a second in the past. So that's mainly what this part is for. It can also publish a TF for the odometry message. So using the position field and the orientation field of the odometry message, it'll create a TF for that. And also publish a stabilized TF, which is the same thing, but with 0 pitch and roll. So only yaw and position, which sometimes useful for planning. So yeah, here's just a quick example. The Gazebo plugin that gives you ground truth state estimate, you have to give it the name of the model, and it will just put that model name or the link name in the child frame ID. But the velocities are actually in the world frame. They're not in the frame of this. And this is not even a TF necessarily. So the core odometry transform launch file parameters is set up so that it just restamps, basically just overwrites those two frame IDs. So now they're both in the world frame, which is the same as the UAV1 map frame in this case. So another package, so we kind of went through all the nodes, but another package is the core Gazebo Sim package. And this is a plugin for Gazebo that just lets you send velocity commands to the simulated drone. It doesn't actually correspond to any kind of like Pixhawk or DJI in real life. It's just purely for sim. And it contains some common sensor setups, some URDF files that you can just include in any kind of drone you're trying to simulate. So it has depth cameras, RGB depth cameras, stereo camera, and planar LiDAR, but also like a Velodyne LiDAR. Yeah, I guess there's a custom Velodyne package in the core stack because the official one is messed up a little bit. Yeah, so here's just some examples of adding sensors, adding a depth camera, adding a stereo camera to your drone frame. And then the next thing is each node in the core stack uses a base main class, which is basically a common way of writing a node, so everybody's node is kind of in the same format. And also for some health monitoring, it's structured in a way so it can just do that under the hood if you use it. And it's also supposed to make it easy to switch from nodes and nodelets. So and the main annoying thing is that if you want to get a node handle and you're running a node, you create this node handle object or a node handle object with whatever namespace. But in a nodelet, those functions don't work. You have to call this other function that's as a separate name. So you couldn't just directly reuse your code. So there's a wrapper function that around those two. So depending on whether it's a node or nodelet, you can use the same function, but under the hood, it will call the right one. So to use it, you basically just have to implement override three functions that you're inheriting from the base main class. Initialize is where you would initialize subscribers, publishers, load parameters, stuff like that, or set up any variables you're going to be using in the class. Execute gets called at a fixed rate based on a launch file parameter. And the rate, like if you set this target parameter to 20 hertz and it's not running at 20 hertz, there's a health monitor that will print an error message if it's running too slow. And then destructors, yeah, you use it like any other destructor. So this health monitor class, so when you inherit the base main class has a member variable that's called monitor. And main uses for these tick and talk functions. So in your code, you would do tick, some name, then you do a bunch of code in between called talk, and then the monitor keeps track of the time difference between the calls to tick and talk. And there's also, I think, a monitor.print statistics function, which automatically also gets called when your node exits. So when your node exits, this database just tells you how fast everything was running that you were timing. So that's how the execute function works. So this is what's happening for the execute function, and that's how it reports if it's not running fast enough. If you just did this, if you just timed TikTok with the name, it doesn't know how fast it intends to run, so it won't print any kind of error message. But if you would add this parameter to your launch file, the name has to match and then underscore target. Then if it's not reaching this hertz, it'll print an error message the same way the execute function does. Yeah, so the core stack is also set up so that you can run multiple drones in the same sim, and none of the topic names or TFs will conflict with each other. So before I set this up, I guess I was always doing it wrong. I was always putting a leading slash in front of topic names, and I've also seen a bunch of other people make similar mistakes. So I just have a few slides describing name spacing. So if, say we have a node that is in the drone controller package, and where the node executable is PID controller, and we're launching it with the name PID control. Launching one instance of it inside the UAV1 namespace, one instance outside the namespace, and say that in the PID control code, we're creating a subscriber for topic 1 and another subscriber for topic 2 with a leading slash. So in that case, the name of the nodes are affected by the namespace. So this node would be called UAV1 PID control. If you did ROS node list, this one would just be called PID control since it's in the global namespace. And if you did ROS topic list, so both of them are doing the same thing internally, but topic 1 would be namespaced by this node, but it would be in the global namespace for this node. So these would be the topics, UAV1 topic 1, topic 1, topic 2. And same thing for parameters. In this case, the parameter is inside the namespace and inside the node tag. So the parameter in the parameter server would be called /UAV1/PID control/P. This parameter would be /PID control/P. So I've seen some common mistakes in looking up parameters because of this. So if you looked up the parameter, so if you create a node handle, this is just your normal global namespace node handle. The node handle with the tilde is private namespace, so it's relative to your node. So in this case, the tilde is basically replaced by UAV1/PID control. So this way, if you ever change the name of the node in your launch file or put it in a different namespace, your parameter lookups won't fail. So in this case, if you looked up PID control/P, it happens to match this parameter. But if you ever change your node name or placed it in a namespace or something, then you wouldn't find the parameter. And if you used to have it outside namespace, it would be confusing and probably not the first place you would look. So yeah, this is the correct way to do it. That's not going to cause issues like that. And just in general, you pretty much never need a leading slash in front of any topics. The most common topics you interact with that are in the global namespace are /ROSOut probably, and /TF and /TF static. And you'd never really interact with these directly. Like you'd never create a subscriber publisher directly for these. You always use these types of macros, or TF, you use these classes which under the hood take care of everything. And I think usually that's the case for things in the global namespace. They're kind of special case type things. So now I'll just talk about how to use the stack, how to get the code and build it, which I probably have already done, and run the examples, which we will do instead during the exercise. And I'll just go over the launch file structure. Okay, so you've already done this part for Gazebo Sim. This is just pure Gazebo Sim, doesn't correspond to an actual drone. And for the PX4 and DJI, you're basically just using different ROS install files. In the Pixhawk case, you also have to do a separate step to build the Pixhawk firmware. So the way everybody uses it, the core stack, is when you need to add some project-specific modification, you just branch off whatever node and then update the ROS install in Core Central. Also, Core Central would be branched off to your project-specific node branch. Also, the master branches are locked, so that just so that nobody unintentionally pushes the master branch. If you have a bug fix or something, you can always send me a pull request, and hopefully I'll merge it in if I can remember to do that. Running the examples, I think we'll just skip this and do it during the exercise portion. So the structure of the launch files in Core Central. Core Central contains everything like the ROS install that you need to pull all the code and build it. and it also contains the launch files for running everything. So there's first this common folder, which contain things that should be run regardless of what platform you're using. And then there's these platform specific folders, like there's one for Gazebo, one for Pixhawk, one for DJI. In this case, there's simulated versions of each of those. So this is the main launch file for a simulated drone. For real drones, I think there are similarly named launch files, but without the sim underscore part. Yeah, so autonomy.launch contains basically all the nodes in the core stack that we talked about earlier. Visualization and launches RViz and the base Station GUI. And then you would put whatever state estimator you're running, like Vinsmono or Loam, in this file without the sim on your real drone. And there's a separate one. So the control is not included in the autonomy because oftentimes you want to tune the parameters different. So you just put that in this file instead. So yeah, now we'll just look at the sim drone. So this is like the main launch file that starts up the drone in sim. So it includes the autonomy and the visualization, and it runs the control state estimation and also spawns the drone. So yes, this Gazebo spawn drone launch file basically loads in whatever URDF you want and creates that drone in sim. And so okay, so there's a few arguments. So there's this robot name argument for the sim drone.launch, but then autonomy.launch, there's also some other parameters in these other launch files that are passed through using pass all args. So this is actually an entire launch file that you would start Gazebo with. So basically you just run a single launch file. It runs Gazebo and it spawns all the drones. So each drone has a parameter robot name that puts everything in that namespace and makes sure the TFs are prefixed with UAV1, so there's no collisions between TFs and topic names between the different drones. And you can also choose, so there's like 3 main parameters. The second one is what interface you want to use. If it's a real drone, you would use PX4 DJI or something. In sim, you can use Gazebo. You can also use a PX4 interface in sim if you're running the PX4 version of the Gazebo simulation. And then you can choose which map representation you want to put into the local planner, either disparity or point cloud map representation. And then choose the position to spawn the drone if you're running in sim. Okay, so now we'll move on to the exercise. So the purpose is to get familiar with the sim and implement some behavior that's using the behavior tree, the behavior executive, and create a node using the base main class. So I'm just going to run. So at this point, we can all run together monlaunch. If you cd into wherever you download the core workspace and do source develop setup, and then mon launch core central. I'll just make it bigger. Gazebo example LiDAR launch. If everybody just does this to make sure it's set up correctly on everyone's computer. If anyone has an issue, I guess you can do the no button in the participants window. So we should also run a ROS core first in a separate terminal and just leave it running. Okay, so the first time you launch this, I think Gazebo downloads some of the models, so it might be a little slow. And it's also just slow, even when they're already downloaded. So just wait for Gazebo to start up. Also, sometimes it crashes. It hasn't crashed. I think it'll eventually work. Maybe not. I mean, sometimes Gazebo just doesn't work and you have to restart it. But it usually does not happen 2 times in a row. So you can see that you're actually getting Velodyne data. There should also be camera data. Gazebo loads the collision boxes first and does the physics simulator. And what's actually taking so long is loading the visuals. So the LiDAR does not actually use the visual meshes as collision. So that doesn't always match up with how the objects look. I don't know. Okay, so assuming it works for you, I guess I should check the participants. It's fine if the GUI doesn't work, I guess. Okay, here, just load it in. Okay, so this is what you should see. Hopefully it's working for you. Just a drone on the ground. So the first time you run this, you'll see the behavior tree here. And here's where the button should be, but the config file isn't loaded. So you should just click open config. And the only option is GUI config. It should load those buttons in. This one's for the fixed trajectories. We don't really need it. It just makes the GUI wider than your screen. So after you select this config, you just want to save it. You don't have to do that every time. And the reason it's not done automatically is because when you save an RQT perspective, it hard codes your name, like your username, into the path. So yeah, so I guess, does anybody have any issues so far? Okay, so if this is working for everybody, then you can click the takeoff button. And you should see the drone flying up. And if you check the behavior tree, takeoff complete is now a success. So after that, you can click explore. And now the drone will fly to waypoints, which you can click in RViz. So in RViz, if you make sure the window is active and press the G key on your keyboard, then you'll see the mouse turns to this green arrow. Then you can just click, and that'll place a waypoint. And then the local planner won't work. It might work for you. I think, I don't know. This didn't happen when I tried it before. Sometimes there can be spurious points, I guess, in the simulated Velodyne. I don't know. Okay, so now it's exploring. But Gazebo hasn't loaded. Just kill the GUI. So yeah, you can just fly the drone around and give it waypoints. So basically this explore action will always say running. There's no criteria for when it's done. On a real drone, you would have some kind of battery monitor or something. So let me just launch it from scratch one more time. So in order to get it to take off and explore, you have to click these 2 buttons. It's not autonomous. And then you have to click the land button. So the task for today is implementing this autonomously explore button. If you have just pulled from master, It doesn't do anything. It was kind of accidentally put in there from sub T. But for the exercise today, we'll just be implementing that functionality to make it take off, go to one waypoint, and then land when it hits the waypoint. Let me just kill the GUI again. So I'm running a version where that functionality is already implemented, just to show you what it should look like when you're done. So I won't show that part of the behavior tree because that's part of the task. Okay, so now it's still taking off. It starts exploring. I just gave it one waypoint while it's taking off, so now it's exploring. When it comes within 4 meters of the waypoint, it'll consider the waypoint hit. Then it should land autonomously when it gets basically towards the end of this path. Okay. So if you click autonomously explore, it won't do anything since it's not implemented yet. So I'll just go over here. Okay, so let me check and see if anybody. So I think nobody had an issue. So except for me. Yeah, so first we'll want to create a node that publishes true or false based on whether the drone is close enough to the waypoint. So we just want to compare the drone's position to the waypoint's position. And if it comes within, say, 4 meters, start publishing true. Then we'll need to add a hit waypoint condition to the behavior tree and also modify the behavior executive to subscribe to this bool from our node that we're writing and update the status of the hit waypoint condition. And then we'll need to modify the behavior tree so that takeoff happens, then exploration happens, and then a land happens. So the first thing we'll do is just create this node that is going to publish a Boolean. So if you go into where you downloaded the core stack, go into the source directory. One of the folders you should see is template node. If you look in template node, there's this node generator script, which basically there's a lot of boilerplate code for using the base main class. So if you do node generator and then in camel case, in this case, we'll just call it exploration. So just make sure that E is capitalized. It might not matter in this case. And then if you just type this and then run and make sure you're in the template node directory, then in the directory above you, it'll create a package called exploration. Oops. So, which basically has a CMake file that's already set up for using the base class. So it's linking to the base class libraries and stuff. And it gives you a source file called exploration.cpp and a header file exploration.h, which basically do all the boilerplate code that you'd need to use the base main class. So it has your initialize function with get node handle and private node handle already created, execute function, and the destructor. And there's a static function you also need for the base main class to work, which you don't have to do anything to. Same with the constructor, you don't have to do anything to that. So now we'll want to add code to this to make it to subscribe to the drone's position and the waypoint and publish whether or not it's close enough to the waypoint. So I didn't really want everybody have to spend a lot of time thinking through that. So basically there's these 4 slides and you have to kind of figure out where to put the code. You can just copy the code in. So here's some declarations, obviously goes in the header file. Here's some code that initializes variables, so you have to decide which function that should go in, either execute or initialize. And here's some code that should be executed repeatedly. So you can also decide which function you think that should go in. And then there's some callbacks, which you just paste into the C++ file. So I'll do that now. And you can also do it. And hopefully it works when we're done. Oh, I did something wrong. Oh, yeah, the one thing I forgot to put in here is the include statements for the message types. So we need standard messages bool. We need geometry messages, pose stamped for the waypoint. For the drones, odometry, we need nav messages, odometry. We should also update the CMake list with those package dependencies. I think I have a slide for that. Yeah, just add nav messages there. And then the package, you can just copy and paste these lines into the package.xml. Now it should build. Oh. Okay, also have to include TF. Include TF, transform data types, I think. Yeah, let me just put that in chat. Then, yeah, we probably have to add TF to the CMake file. And the package. Okay. Oh, I copied and pasted. Copied and pasted this line twice. Yeah, I don't actually need this. Okay, I should mention we're checking the distance between the waypoint and the drone's odometry. They happen to just be in the same frame. So we don't, I mean, if you were writing this for real, you would want to check, you'd want to do the transform, which I was originally doing, but it's just more code. So you should just delete the transform listener from your header file, unless you really want to do it. Okay, so I guess I'll wait to make sure everybody has their expiration node. I also added, yeah, if you don't feel like typing that out, you can pull this node, which has it already in there for you if you want to. you can pull this if you don't want to do what we just did. Yeah, I guess people can give a yes check mark when they're ready to go to the next step.
Maybe if somebody has problems, do you want to kind of ask where you hung up? Do we have more than Andrew?
Yeah, I'll just also show, I mean, you can just clone it from GitHub if you want, so you don't have to copy and paste everything. So I just deleted the stuff. And if you just clone from this repo, Should be exactly the same. Oh. Well, it works in this. Maybe since I recompiled with a different folder name. Oh, yes. Okay. Yes, it wasn't happy about the package name being the same, but the folder name being different. So I guess if you cloned it in, might have to do a clean rebuild. Also, there's a branch of Core Central. You should be on the master branch right now, but there's also a Tutorial Week 2020 branch that is basically the solution to the exercise we're doing right now, in case you wanted to just look at that afterwards or something. So I'll just wait till this builds and I guess move on to the next step. And yeah, if anybody has any questions or something isn't working, you can let me know. So the next step would be actually, we have the node, but we want to make sure it's in the right launch file so it's actually getting run. So when you did that template node, when you generated this package, it also automatically generates a launch file that launches whatever the node name is with the execute target set to 20 by default. And yeah, no other parameters. So we don't need any parameters. So this launch file is fine. We just have to include it at the right place in Core Central. So Core Central launch. So the right place would be the common folder in the Autonomy launch file. Yeah, there's these different sections. Probably behavior is a good one. Okay, so if you add that to your launch file, should be able to run the demo again. Probably have to resource since you added a node. So is it running? Yes. Okay, so if you give a waypoint in RViz, then if it's running, it should start printing the distance on the terminal, the distance between the drone and the waypoint. So if that's happening, the node is probably working. Hopefully the Boolean is also being published correctly. So the next step is modifying the behavior executive to subscribe to that Boolean and then publish the status of a condition so the behavior tree knows what's going on. So if you go on core behavior executive behavior tree.cpp, and also open the header file. So basically we need to create a condition called, I guess we'll call it whatever the name of the subscriber was, hit waypoint. We'll just call it hit waypoint condition. hit waypoint underscore condition in the header file of behavior executive. Okay. And then we need to instantiate it over here. So this constructor for a condition just takes in the name of the condition as it will appear in your behavior tree config file. So we just need to make sure that this string here matches what we're going to, in the future, put in our behavior tree config file. And for the behavior executive, we also just add all the conditions to a list, and it iterates through this list and publishes them, so you don't have to call publish by yourself on each condition. But you do have to remember to add it to this list, otherwise it won't publish anything and the behavior tree won't receive anything about it. So you just have to do conditions.pushback hit waypoint condition. So this sets the condition up, but now we need to set the condition to true or false based on that Boolean that's being published from the node we just created. So we need to create a subscriber, hit waypoint subscriber. Basically, this is the same pattern as most of these other subscribers here. So like isArmed is basically just doing the same thing, listening to a Boolean. Hit waypoint. So, and then there's a section in the initialize function where we create all the subscribers. So we just need to add one for hit waypoint. And the topic is hit underscore waypoint. And callback. Okay, so then if you've done this, we're done with the initialize function. So we just need to create the hit waypoint callback, which is basically doing the exact same thing that isArmed or offboard or a lot of these things are doing. Just want to make sure. So we're setting the hit waypoint condition to true or false based on what's in the Boolean message. Okay. I have a question from somebody on Slack about the demo. Wait, this is somebody that is here right now, right? Yeah. Okay, so it's not finding the base node. Wait, did anybody else have a compiler error when you did CAC and build? Sometimes. I'm not totally sure why that would happen.
So I think that's due to an issue that I found before that I opened a PR for in Core PID controller. What I think that is because there's in the CMake list, there's a find base, but the problem is that Core PID controller actually doesn't use base because it's not a node, it's just a library. And so it's trying to find a package it doesn't need. So if you just remove that find package comment, it should be fine. The other thing is you might also need to remove it from the add dependencies line too.
Yeah. I'm just commenting everything out. I guess that has a base in it. For me, it compiled, so it might be hard to tell.
For me, I have two Cascade workspace use this package. So you see that it find another folder for containing the same package. So I don't know how to deliver the second one. The first line is that what I'm using, like the AirLab tutorial workshop here, but the second one is a different folder. So maybe at that folder, I also have a package.
Oh, okay. Maybe are you sourcing a devel setup file maybe in your bash RC?
Okay, let me check.
Or I'm just wondering if somehow the source, the devel setup got sourced from that other workspace.
Well, if you're using Cactus build should automatically extend the other workspace, and the way extending will work, it'll just ignore the older version. It would use whatever is like the most whatever you extend, right? It uses like there's like an order of precedence.
Okay.
But so I've seen this if you build core PID and like with a completely clean CMake cache, for example, it'll come up with that error. So it depends on your CMake cache and order things get compiled, or whether or not it'll come up with that error.
Okay.
Ian, I can also send you a Docker
really
file to if you want to run all this within Docker.
Okay.
Yeah, I guess, does anybody have any questions about the modifications we just did to behavior executive? You can also pull the branch on behavior executive tutorial week 2020 if you just want to get the changes I just made. Yes, so then the final step is actually modifying the behavior tree configuration file to take off, putting the conditions and actions in the right order so it'll take off and then explore until it hits the waypoint and then land. Yeah, I don't know if people want to try to figure that part out themselves. I guess it depends on if everything so far is working or not. I guess I'll just do it, and you can either cheat or do it yourself. One thing, you have to make sure that these are tabs. If it's some other form of white space, nothing will work. And basically, we're just kind of sequentially doing what the other buttons are doing. So you can kind of copy from the other buttons. sure if this is correct. I don't really remember. Okay, so yep, that was everything. So this is the modification you'd have to make. So the arrow is trying to do each one of these things sequentially, and its children all have to return success. So the first step is a takeoff, basically. And the question mark, only one of the children have to return success. So when it's on the ground at first, takeoff complete is false because it hasn't taken off. So this returns false. And then the takeoff action is set to active. It's running. When it reaches the takeoff height, the action returns success, but also the condition becomes success. So this is successful. And it basically moves on, going back up to the arrow, move on to this section, which is, it's the same pattern. Hit the explore until the waypoint is hit. And then the last thing is also the same pattern. Do a landing action until the drone is landed. Yeah, so you can also check out Core Central and go through the same build process that you did to set up the master branch and run everything, and it will do this behavior that we implemented right now if you want to skip everything and just see the behavior. Yeah, so that's it. If anyone has any questions, otherwise we're done. Thanks.